Hello, everyone. It looks like it's just me today. So I'm going to give a very quick overview of the Module 11 t-test for two related samples, or the repeated measures t-test, or the paired samples t-test. There's a few different names for it this week. I've got a picture of two little twins here. Pretty adorable. They're related in one way or the other. So the good news is this test is essentially a one sample t-test. So I'm going to speak very quickly about the test in general, and then we're going to go ahead and do a hypothesis test. So nobody's here today. All right. So I'm not going to ask you what your questions are, but please know that you can always bring them to me. All right. So we've got this growing family of hypothesis tests. We've been talking about this when we had one sample and we knew the mean and the standard deviation of the population. We could do a z-test. That was easy. But sometimes we have one sample that we're comparing to a population, but we don't know the standard deviation. And in that case, we need to do a one sample t-test or a single sample t-test. And last week, we had the situation where we had two samples, but we didn't know anything about the population. We had to estimate the standard deviations and means of the population based on the sample. We did the independent samples t-test. This week, we have a different type of a sample. It's a sample where we have two sets of linked data points. So in a way, we know the mean of the population, kind of, and I'll explain that. And this is called a paired samples t-test or repeated samples t-test or related measures t-test. Basically, whenever we have two sets of data that are linked together. So here's one situation where we might have two sets of linked data points. So let's say that you have a bunch of subjects in a study or people in a study, and each person provides two data points. Maybe it's a pre-test or a post-test. So for example, subject one, that might be me. Let's say it's me. I have a score on assessment number 1, A1, and I have a score on a separate assessment. We'll call that B1. So I have maybe a pre-test and a post-test. It's linked together because both scores are for me. And maybe number 2 is you, and you have a score on the first test and a score on the second test. So this is called a repeated measures or within subjects design. So here are some examples of when we might have two sets of linked data points with one sample. So one sample meaning same set of people, but each person has two separate data points. So maybe we're looking at each subject's memory score before and after taking a supplement for a period of time. Maybe ginkgo biloba or some supplement is supposed to help us to have better memory. So we can take a pre-test, administer the supplement, and then do a post-test. So my scores on the memory pre and post are linked because they're both about me, and your scores are both about you. Maybe we have a math test before and after a math lesson to see if the math lesson worked. And maybe we're looking at how much people grow over time. So we're looking at people's height at 18 years old and 21 years old. I don't know if much growth actually happens between those years. And then maybe we measure each subject's energy level in the morning and in the afternoon to see if there's a difference. So same person, but measured two different times. So that's situation number 1. This is the type of situation that we're going to be dealing with most in this week. And basically what we're looking at, is there a significant difference between the two measurements? All right. So in situation number 2, we can have two linked samples where each subject in sample A is linked to a subject in sample B. So now we have two subjects, but the subjects are linked in some way. So maybe we have a father and a mother of a child reporting reading time with the child, and we want to know if there's a difference between those two things, father and mother. Husband and wife are reporting the amount of sleep, so their scores are linked together, and we're looking for a difference between their scores. A mother and a daughter are measured on an IQ test, or a memory score from a Parkinson's patient is matched up with a control subject with comparable demographics. So sometimes we do that. We find somebody that matches the patient in every way, shape, or form, except for they don't have Parkinson's, and we see if there's a difference there. So we're still looking for a significant difference between two measurements. So where's the DSM in this case? So let's just talk about a scenario first. Let's say we have 20 pairs of monozygotic twins, so identical twins are included in a study. But each of these twins have been adopted from birth into different families. And the researcher wants to know if there's a difference in their IQ scores. So this is kind of a nature versus nurture question. If nature is strong, their IQ scores should be similar. But if nurture is strong environment, then their scores might be different. So the twins of interest are the population of interest are monozygotic twins adopted separately, but there's no population to compare these scores to. So where do I get the population mean for calculating the T, and how do you compare two samples and the populations behind them without a separate comparison population? We can do this. I'm going to show you how. Because each score can be directly compared, we're going to calculate a different score. For each set, we're going to have a different score. And that's going to result in one set of different scores. That becomes our sample. So yes, we have maybe the sample of each pair of monozygotic twins, but the different score between them is what we're really going to be calling our sample. And thus, this becomes a one sample t-test. So this is an illustration of what we're going to be doing. So for pair number one of the twins, the first twin has a score, the second twin has a score. We do a quick subtraction of these two scores to find a different score. Okay, so now we're going to have a sample of different scores, basically. So are the twins different in IQ score when raised in different home environments? The null hypothesis is going to be there's no significant difference in IQ score if they're raised in different environments. And the way that we write the null hypothesis for this repeated measures or related samples t-test is the mean of the different scores is going to be equal to 0. So I'm going to go back and just say that if we were to add up all of the different scores here in this last column and average them out, if there's no real pattern to a different score, for example, there's not a big difference between sample A and sample B, then on average their scores are going to be 0. That's not saying that every score is going to be 0, that there's going to be no difference between the twins, but maybe some are higher, maybe some are lower, but when you average them out, it averages to 0. There's no systematic difference one way or the other. So the alternative hypothesis is that there is a significant difference in the IQ scores. And the way that we write that is just the mean of the different scores is not equal to 0. And just as a reminder, we're using the mu symbol because we're talking about a population. We're making a hypothesis about a population. Even though we're dealing with a sample, the hypothesis is about the population. So the comparison population where the sample comes from, if the null hypothesis is true, would have a mean of the different scores of 0. So that's the null hypothesis. If the null hypothesis is true, then if you average out all the different scores, it's going to be 0. So the comparison population, the DSM, is going to have a mean of 0. All right, so here we go. We're going to compare the sample of different scores to the population of different scores that have a mean of 0. And the way that we do this is we just take the mean of the different scores and divide it by the standard error of the difference scores. So this is how it's like a one sample t-test. So we're going to calculate the sample mean of the difference scores first. And according to the null hypothesis, the population mean is 0. We're going to estimate the population standard deviation, much easier this week. And the way that we do that is, you'll recognize this from the single sample t-test, the square root of the variance divided by n of those difference scores. and we'll calculate the t-statistic. So we've got this. We can find the critical t, compare it. All of this is similar to what we've done before. So let's do a few practice items. These are items that might be on part 1 of your practice assignment. So if we have a repeated measures t-test, it has a sample of 15 participants, and the sum of the different scores is negative 45. What is the mean of the different scores for this sample? So you might be given the sum of the different scores and the n, and you have to figure out then what the mean is, but you can do this. We've done this 100 times. The mean is going to be the sum of all the scores divided by the n. So the mean of the different scores is the sum of all the different scores divided by n. So in this case, the sum of the different scores, if you take all the differences and you add them up, is negative 45. The n is 15. So the mean of the different scores is negative 3. That means that there is a systematic sort of, well, we don't know if it's statistically significant, but on average, there is a difference of negative 3. Okay, so a repeated measures t-test is a sample of 26 participants with a mean of the different scores of 3.75 and the sums of squares of 450. What is the variance for this sample? So I'm going to give you the sums of squares. You don't need to do that, but you might need to figure out the variance. This is just stuff we've done before. The formula for the variance is the sum of squares divided by, in a sample, n minus 1. So here we go. There's the formula, so you just plug it in. The sum of the squared deviations was 450. N minus 1 is 26 minus 1 is 25. 450 divided by 25 gives us a variance of 18. Why am I having you figure out variance right now? We're going to use variance when we're figuring out our standard errors. So just a reminder how to figure out variance. All right, a related samples t-test was conducted for an SAT prep class program. A total of 35 participants were recruited. And the study ended with a mean of the different scores of -4. What does this tell you about the study? So sometimes you get a question like this and, well, you don't know, you can't do a related samples t-test because you don't have enough information. But what this tells us, if the mean of the different scores is -4, is that there is a systematic difference between the two scores. So we do know that. Okay, here's an example of a paired samples t-test, two-tailed at alpha 0.05. And this is just like your part 2 assignment. So walk through this with me. You'll see how easy it is. You can do part 2. 9 students completed an SAT math preparation course before taking the SAT math exam. So they were tested on their math proficiency before and after the SAT prep course. So we want to know if this prep course worked. And one way to figure that out is to do a pre-test and a post-test, and in the middle, give the SAT prep course and see if it makes a difference in the scores. So this is perfect for a paired samples t-test. And so the question I'm going to ask is, do students score differently on the SAT math section after taking the prep course compared to their school's scores before taking the prep course? So we're going to write our hypotheses. And so the question is, do they score differently after taking the prep course? And my null hypothesis is going to be that they're not significantly different. The scores are not significantly different pre and post. My alternative hypothesis is going to be, yes, they are different. I'm not saying that they're going to be higher. I'm not saying they're going to be lower. I mean, maybe doing the prep course somehow makes you worse off. Not very likely, but there you go. So our critical boundaries, the degrees of freedom for a paired samples t-test is n minus 1. And you might be thinking, but you have 2 different measurements. So why isn't it n minus 2? Well, because remember that what we're testing is the sample of different scores. So we only really have one sample, and that's the different scores. So it's going to be n minus 1. So we had 9, I think, right? So that gives us degrees of freedom of 8. We had 9 participants. And proportion in two tails combined at alpha 0.05 gives us a critical value of 2.306. But it's not just 2.306. It's plus or minus 2.306. All right. So how do we do our calculations? You're going to be given the mean of the different scores. You don't actually have to do this, but I'm just going to show you how it would be done. So let's say that these are the math scores before the prep course. Here we go. And the math scores after the prep course. There we are. And then we take the different scores. Now, here's where order really matters. We want to start with the second score and subtract the first score. And that way, if I end up with a positive number, I know that that's good. The prep course worked. So for example, the post-test is 760, the pre-test is 690. So if I take 760 minus 690, I have a positive difference of 70 points. I gained 70 points. It really helps with interpretation. So you're going to take the second score in this series and subtract the first score. And sometimes it won't matter. But like, for example, if you have a husband and a wife that are reading to their children and you're looking for just a difference between those, unless you're looking for a gender difference, I'll back up. Always do the second score minus the first score. All right. So what we have are a set then of different scores, 70, 10, 50, 50. That is the new sample. The new sample is the different scores. If I add up all of these scores and divide them by 9, because that's how many are in the sample. I already did the calculation for you. We have a mean of the different scores of 30. So that's our average. Now, you are also going to be given the sums of squares, but I just want to remind you of what it looks like to find the sums of squares of a set of different scores. So these are the different scores for each pair that we just figured out in the last one. And we just find the sum of squared deviations from the mean, just like we've done before. Again, you're not doing this. I'm going to provide you with the sums of squares, but we take the mean of 30, we take each score minus the mean, and then we square it and add it up to get the sums of squares. All right, so we need the sums of squares to be able to figure out our variance. Okay, so the formula for variance is sums of squares divided by n minus 1. If you added up all these sums of squares, it was 4,000. We had 9 in our sample, minus 1 is 8. 8 goes into 4,500 times. So our variance is 500, and we need that to be able to conduct our test. Now again, you're going to be either given the sums of squares or you're going to be given the variance, maybe even. You're going to be given the mean differences. You're not calculating any of that, but I wanted to show you how to do that. All right, so we're going to do our calculations. You're going to be shocked at how easy this is. So I up in the corner have the mean differences, which was 30. We figured that out. The n was 9. We just figured out the variance is 500, and that's all we need to have to be able to figure out the repeated measures t-test. So the formula for the standard error of the different scores is the square root of the variance divided by n. That's just like for the single sample t-test, right? So the standard error for the mean of the difference scores is the square root of the variance divided by n. We've got all this information already, so I'm just going to plug in my variance is 500, my n is 9. That gives me, if you put 9 into 500, it gives you 55.56. Take the square root of that, and your standard error is 7.45. So could not be easier, right? Your t-statistic is calculated with the sample mean, the population mean, and the standard error. So I've given you the sample mean. Remember, the sample mean is the mean of the difference scores. And the population mean we know to be 0 because if the null hypothesis is true, there's no difference. So that's always going to be 0. The standard error we just figured out. So here we go. We have the mean of our different scores minus the population mean of 0 divided by the standard error. Now, you can actually just write this, the mean of the different scores divided by the standard error. So this is sort of formal here to write it this way, but the mean of our different scores was 30. The population's always going to be 0, so we don't need to include that. divided by our standard error of 7.45 gave us a t-score of 4.02. Now you remember what our critical value is. You can kind of figure out where we're going with this. Okay, here's another way, as I mentioned, to write it. The mean of the different scores divided by the standard error. Okay, your last step in trying to figure this all out is to make a decision. You're going to compare the t-statistic with our critical value. Now, our critical value was plus or minus 2.306, but our t is positive, so we're going to compare it to 2.306. And my t is indeed larger than that critical value. The result is significant. I'm going to reject the null hypothesis, and this is how I'm going to write it up. A study was conducted on the effectiveness of a SAT SAT prep program. And this is the statistical notation. T in parentheses, the degrees of freedom of 8, or T in italics, degrees of freedom of 8 in parentheses equals 4.02. P is less than 0.05. I know that because it's more extreme than the critical value. I'm going to reject the null hypothesis and say that the SAT prep program did make a difference. So that is it. What a test. No, it's not it. We need to do the effect size. Okay, so effect size is going to be similar in format to what we've done before. The Cohen's d for a paired samples t-test is the mean of the different scores divided by the standard deviation of the different scores. Okay, so that's different. The mean of the different scores is 30. And we've already figured out the variance, but we can plug everything into this formula. So the standard deviation of the different scores is going to be the square root of the variance, basically, of the different scores. We knew a couple different things. We knew our sums of squares was 4,000. We knew our n minus 1 is 8. So we can just plug that in. 4,000 divided by 8 is the square root of 500, because we already figured out the variance was 500. And it gives us a standard deviation of the different scores of 22.36. Just plug that into the formula. Our mean of the different scores was 30. The standard deviation of the different scores is 22.36. So the Cohen's d in this case is 1.34. That's pretty hefty. That's huge. All right, large effect size. All right, I would ask you if you have closing questions, but you're not here. So please bring questions to me. I'm here to help, and I want to help, and I hope that you enjoy this type of t-test.